Hello everyone, hope you all are doing well. So here we are with a new video with the last part of ratio of specific heat. So up till now we have done specific heat capacity, the ratio of specific heat capacity for monoatomic gas, and in diatomic gas we had done two, that is rigid rotator and the other was non-rigid rotator for the diatomic gas. In case you haven't gone through these two videos, just a request to go 3 videos back and follow the lecture series. Anyway, so today we are about to study this ratio of specific heat for polyatomic gases. So this is a polyatomic gas, like there will be more than 2 atoms in a molecule. So let's say this is one atom, this is another atom, and this is the third atom, and they are connected between them in a bond. So you'll say, so why are we not doing here rigid and non-rigid? Because if the number of atoms in a molecule exceeds 2, then the gases do not behave like a rigid rotator. The molecules do not behave like a rigid rotator. So the molecules will always have a vibrational mode if you have 3 atoms or more than 3 atoms or 4 atoms or whatever it is. That's why we do not segregate into rigid rotator and non-rigid rotator for polyatomic gases. But this is not true for a diatomic gas. That's why we had done in a diatomic gas segregated it into rigid rotator and non-rigid rotator. So today we are going to consider a molecule which is something like this, which I have shown this in the box. There is this one atom, there is this another atom, there is a third atom, and the atoms are connected in a kind of a spring model. And yes, these molecules can move in the x direction, y direction, as well as the z direction, x, y and z. So it has 3 translational degrees of freedom, and this molecule can rotate in all 3 kinds of axes, x and y and z, x axis, y axis and z axis. So it can rotate in x, it can rotate in y, and it can rotate in z. And nowhere the moment of inertia is going to go 0. So never the moment of inertia will be 0 for a polyatomic gas which has a molecule which is of kind of this shape. Okay, these are called as non-linear molecules. Like the atoms are not in a line, they are not in a line, they are non-collinear. So in this case the molecule can rotate around x axis, y axis and z axis. So it has 3 rotational degrees of freedom. And just to keep hand on this, that maximum rotational degrees of freedom can be 3, maximum translational degrees of freedom can be 3. Okay, yes, but had this molecule been somewhat like this, it is a polyatomic molecule, but this molecule is having a kind of one axis where the moment of inertia is going to 0. Okay, I'll just redraw it by a pen. Let's say this is one molecule, this is another an atom, and this is the third atom, and this whole set, the yellow color thing, is a molecule, polyatomic gas. Now it can rotate if you rotate this molecule around this axis, the moment of inertia goes to 0, and these molecules are called as linear molecules. These are linear molecules. So these are linear molecules. However, these molecules, the purple one, this is called as the non-linear molecule. Non-linear molecule. Okay, so yes, we are supposed to take care whether the gas is having a linear molecule or a non-linear molecule. I'll erase the parts. I'm considering right now the shape of the molecule as this way. Okay, so let's get back. Now in this case, in this molecule, we can have because there are 3 bonds here, we can, because there are 3 bonds, 1 bond, second bond and the third bond. So the molecule can vibrate like this, the molecule can vibrate like this, and the molecule can vibrate like this. So it has 3 vibrational degrees of freedom. But yes, this vibrational degrees of freedom in this molecule is 3. But yes, if the atoms were in a single line, then the molecule could have vibrated like this or like this. So in this case, if you see, there are only 2 vibrational degrees of freedom. Even the atoms are 3, but there are 2 degrees of vibrational degrees of freedom. In this, there are 3 atoms, but still there are 3 vibrational modes. So I have just said F vibrational modes because it depends upon the structure of a molecule. Now, once you are through with finding out the degrees of freedom, you are almost half the part is done. Now, kinetic energy per unit molecule is given by. Now, in our previous videos, we have understood that each degree of freedom brings in half kBt. So 3 translational will bring 3 half kBts, and 3 rotational will bring 3 half kBts, and F vibrational modes. So now in vibrational modes, again we have understood that one mode brings in 2 half kBts, 1 half kBt for kinetic energy and 1 half kBt for potential energy. So if there is a single vibrational mode, if there is only a single bond, then you have 2 times half kBts. But if I have F vibrational modes, so in that case I'll have an F times 2 times half kBt. Mind you, in this 2, one is for kinetic energy and the other is for potential energy, and that signifies for a one spring, okay, one bond. Now if you structure out this particular molecule, then because there is a 1, 2 and 3, there are 3 bonds where there are 3 kinds of spring. So I should have written a 3 over here. So half kBt plus half kBt for this one, and same way half kBt for this one, and half kBt for this one. So that would have been 6 times half kBts for this kind of molecule. But yes, the molecule structure will determine how many half kBts would it have. So coming back to the derivation, this is kinetic energy per unit molecule, so divided by n, and I have just taken half kBt common from each term. So what remains is 3, 3 and 2f. So 3, 3 and 2f. 3 plus 3 will give me 6 plus 2f, half kBt as it is. I have taken 2 common from this term, so I'll get 3 plus f because 2 is common outside. This is half kBt. Again, the process remains same. If you have been following my previous videos, then the process won't change. So I'll see that n is the number of moles, capital N is the number of molecules, and capital N is number of molecules, and Na becomes our Avogadro's number. So keep n on one side, take this Na on the other side, so you get capital N is equal to n times Na. Put this n ka value over here. So I would get U upon n times Na equal to, everything remains same on the right hand side. Just pull this Na on the other side, so this Na goes here. So what was Kb here, it is now Na into Kb, and kinetic energy per mole, this is just kinetic energy per mole, and this was kinetic energy per unit molecule. Now Na into Kb is nothing but R, that is the universal gas constant. So wherever there is Na and Kb, I have just simply removed it as R. Now I am going to differentiate this with respect to temperature. So differentiating with respect to temperature, I get du by n dt. N is a constant, that is thrown outside. 2, 3 and f is a constant, that is thrown outside. Half is a constant, r is a constant, and then I get derivative of t with respect to t. This value comes out to be 1. So we do not write 1, we just ignore that part. Yes, 2 and 2 gets cancelled, so I get 3 plus f into r. So this becomes my one of the equations. So this becomes my Cv, that is that is molar specific heat at a constant volume. Then comes the Mayer's equation. We have also derived this in our previous videos. If you haven't gone through, then would request to go through this derivation of Mayer's equation as well. So Mayer's equation is Cp minus Cv is equal to R. This is what is called as the Mayer's equation. So with Cv known, I can find out Cp. So Cp would be equal to R plus Cv. Cp would be equal to R as it is. Cv ka value I have to put it from here. So that is 3 plus f into R. So I have taken R outside common. If I take R common outside, I'll get 1 over here plus 3 plus f, and R goes outside common. So I get 3 plus 1, that is 4 plus f, and R common outside. So now gamma. So this is your molar specific heat at a constant pressure. Now the final step, that is the gamma, that is the ratio of specific heats. Now the ratio of specific heats is Cp by Cv. So we can just put the values of Cp and Cv. R and R gets cancelled. What remains is 4 plus f upon 3 plus f, and this is for a polyatomic gas. So you see, we just derived for all kind of molecules, monatomic, diatomic, polyatomic, and yes, here you should take care that if the molecule can become of any shape, like I can just play with this. Suppose this is one molecule, this is another molecule, and maybe this is another molecule, this is another molecule, like this. Okay, this is another molecule. So now this will have 3 translational degrees of freedom, plus it will have 3 rotational degrees of freedom, because it can rotate in any possible directions, and the moment of inertia is never going to go 0. And it will have 2 vibrational modes. So accordingly you can calculate. I have given you an example of linear molecule as well. So if I have a molecule here, I have a molecule atom here and a atom here. So this will have 3 translational, plus it will have only 2 rotational, because the moment of inertia around this axis, is going to go 0. That's the reason we are not considering this rotation. And yes, vibrational mode, there are 2 vibrational modes because there are 2 springs. So this is one spring and this is another spring. So you can just imagine of molecules of lots of different shapes, and you just keep on applying the same concept, and you can just keep on finding out the gamma, that is the ratio of specific heats. So you can find out specific heats for a particular kind of a gas as well. So that's all for today. I hope you have followed this video, and entire article for the ratio of specific heats. So tomorrow onwards we will be discussing about coefficient of absorption, reflection and radiation. So in case you haven't subscribed my channel up till now, I would suggest you can subscribe. You can also comment. I haven't received any comment as of yet. I would really appreciate if somebody comments for the first time and lets me know, okay, what kind of videos do you wish to see, or what kind of difficulties you are facing while you watch my videos. Thank you so much. Please subscribe and like the video and share the video. Thanks. Bye.